Welcome to Brain Vision.
So here in this problem we are given a propped cantilever beam of length L and a concentrated load of magnitude P is acting at a distance of small a from the fixed support, and we have to calculate the reactions RA, RB and MA, that is a moment acting at point A for the given beam. And we have to also draw the SFD and BMD, and we have to label the critical ordinates. Now, to solve this problem, we'll be using the superimposition principle, and if we consider that this support is not there, then the deflection would be like this. It would behave like this. And now if we consider that this is not there, but is acting on this image, if we consider that this is not acting, then the deflection diagram would be like this. Now let us make more schematic diagram of the deflection. So this is the deflection curve when we assume that the reaction force RB is not acting, and this deflection delta B1 we can obtain from any of the book. This formula we have PA square over 6EI times 3L minus A, where L is the total distance of the beam, this total distance L, and A is the distance at which the point P is at which the load P is acting. Similarly, if we consider that the point load P is not acting, then the deflection would be in the upward direction, and its formula would be equals to delta B2 will be equals to RB. RB is a reaction here, L cube over 3EI. Now we can use the compatibility equation to calculate the value of RB, and by using the compatibility equation we can say that the deflection at point B should be equals to 0. So it will be equals to delta B1 minus delta B2 will be equals to 0. So from here delta B1 we have this much, so we can plug it here. PA square times 3L minus A divided by, this is 6EI, minus delta B2 we have this much, so we can plug it here. RB L cube over 3EI, and it is equals to 0. So from here we can easily calculate the expression for RB. So RB will be equals to PA square times 3L minus A divided by 2L cube. So this is the required expression for RB. Now next I will be calculating the expression for RA and MA. For that we will be using the equilibrium condition of the beam. Now we'll be equating the forces in the vertical direction, that is sigma Fy is equals to 0. Now the forces in the downward direction will be taking it to be positive, and in the upward direction will be taking it to be negative. So we have minus RB minus RA is equals to P. So from here the expression for RA will be equals to P minus RB. Now we can plug the value of RB here that we have calculated earlier. So P minus RB is PA square times 3L minus A divided by 2L cube. So from here the expression for RA will be equals to PB times 3L square minus B square divided by 2L cube. So this is the expression for RA. Now next I will be calculating the moment MA. For that we'll be using moment equilibrium equation, or we will be taking the moment about point A equals to 0. So we'll be taking moment about point A, and the moment about in the anti-clockwise direction we'll be taking it to be positive, and the moment in the clockwise direction we'll be taking it to be negative. The first moment which is acting at point A is MA, that is the reaction force, a reaction moment. So MA Since it is in anti-clockwise direction, we are taking it to be positive, minus this, the moment due to this force would be 0 because it is passing through point A. So minus P times A, and it would be plus RB times this total distance is L, and will be equals to 0. So from here the expression for MA would be equals to PA minus RB into L. Now we have calculated RB, so we can plug it here. So PA minus RB, we have PA square times 3L minus A divided by 2L cube times L. We have plugged RB here and rest as it is. Now we're going to simplify this and we'll get the expression for MA is equals to PAB times L plus B divided by 2L square. So this is the expression for MA that was asked in the question. Now next I will be drawing the shear force and bending moment diagram of the beam. So this diagram is for shear force diagram, SFD. Now this magnitude represents RA, and this vertical magnitude, it represents RB, and this is positive and this is negative, and this distance is A, this distance is A, and this distance is B. And now where the shear force is changing its sign, there the moment would be maximum, and this magnitude, this vertical magnitude of the moment, is given by M is equals to RB times B, and this vertical line represents the moment MA, and this is the point where the shear force, the bending moment is changing its direction or sign. This moment is positive and this one is negative. This is bending moment diagram of the beam. So this is the final answer. So I hope you have understood the problem. Thank you.